Welcome back. In this video, I'm doing the Leetcode question, and for today, that's 145 binary tree post order traversal. It's an Leetcode easy. Okay, given the root of a binary tree, return the post order traversal of its nodes values. Okay, example one, we have 1, 2, 3, and post order should be first left, then right, then root. So until the end. So first we got left, right is nothing, root, and so on. So it's 3 to 1. Okay, okay, the number of nodes. And follow-up is iteratively. Okay, let's do the recursive solution. We ain't gonna do C++, but Python. Okay, so we need to track nodes in right order, and for that I'm gonna do result, and I'm going to define post order, which will take node, and what will it do if node if not node, so if node is null, it will return else. So for post order, we first want to check out the left. So post order, we'll call it on the left node. So node left, post order node goes right. Okay. And then we have to result append node value. And then we just return result, plus we need to call post order of root. So let's check it out. So result, that's what we are going to return. We start with the root, so we start with the 1. It's not known, so it will continue. First we're going to call the left part. Here it's null. Then we're going to call the right part, it's 2. And then we are going to continue on the right part, because that's the first place we're gonna do this. So when we are on the node 2, so this one, we go to the node 2, it's again not null. We'll call on the left, that's 3. And we see the 2 doesn't have the right child. So on the node 3, we don't have node left, node right. That will just return. And here we'll append 3. Then we're going to return back from here. Node 2 doesn't have a right. We'll append the value 2, and same for the value 1. So that's kind of logic. I think it's not that hard, so you should catch it. Let's try to run this. Okay, so 3 to 1, 3 to 1, submit. And it's okay. For the time and space complexity, so we need to visit each node once. So call FR, yeah, that's often. And we also have ONF space for results. So time complexity of n space of okay. And let's check. So the recursive solution. So this was recursive solution. Let's check the iterative solution. I'll just delete this. So how can we do the iterative solution? First, we need to take care of like so the difference between recursive and iterative solution is that we need to implement that recursive part of uh, of memory, so of stack, to make it iterative. So for that, I'm going to use two stacks to do the same thing. Stack 1, stack 2. First stack will process the nodes in such order that when we add the node we visit to, so we'll process nodes through stack 1 and we append them to stack 2. You'll see what's the idea. So first we need to add stack 1 root, and what do we do? So whilst there is something on stack 1, we need to pop it. So node is equal to stack1.pop, and we're going to push this value of the node to stack 2. So node, or we can push the node. It's better to push just to okay. To stack 2 dot and node dot value. Okay, and what do we do now? So we added the value of the, let's say, 1, because that's the root node, to the stack. So what do we need to do next? We need to call, we need to like continue with the same idea. So Postorder, in such sense that first we need to visit, since we are doing like in reverse order, so in this stack 2 all nodes will be like reversed. So we'll need to do first, and we are popping, so we're taking the last element. We first need to push to stack 1, so stack 1 dot append the left node dot left node dot left, and then node right, because when we pop, we're gonna first pop the right node. So stack. Okay, sorry, someone was knocking on my door, so I had to check. Let's continue. So I appended this node to stack 2, and stack 2 will be in a reverse order of so Postorder traversal. So first we're gonna put node, like in this example, we'll put 1. Then next thing we're gonna put 2, and then we're gonna put 3. We would put this one if we had this one, and then 3, but we don't have it, and so on. So how do we do it? Let's say children to stack 1. Okay. So node 1, node from stack 1, that's like some node. We put its value to stack 2, and then we append left node and right node. Why that way? Because that way we are going to, when we, this way when we also need to check if, how do I need to check it here? If not left, then okay, let's do the if not is none. So if root, or if not root, we just return, or do we just return this. And here, let's check it like this. So if node dot left exists, node dot right exists. In this way, let's say we have both left and right node. We're first gonna, in next iteration of stack, visit right node and then the left node, because we are doing the reverse order. Okay, and this is not step 2, but step 1. So step 1, we append, that should be it, and we should be able to do it like this, return stack 2 reverse that exists. Okay. Run stack 2. Okay. So just drag this in place so it doesn't return anything. Oh, let's try now. And it's accepted. Maybe reverse is not what we. Maybe this can be faster, but yeah, it's okay. It works. Not to delete it. So, and for the time and space complexity, it's the same. So time complexity of n, because with step 1 we're gonna go through all elements of the tree once, all nodes once, so that's n. And for the memory we have just 2 times of n, so that's again of n for the space complexity of n. Okay, I hope this made sense. Thank you for following in this one, and see you in the next one.